Hello everyone. I'm Tianyu Ren from University of Illinois Urbana-Champaign. Again, I'm advised by Professor Houtan Jebelli. So my second paper is about the advanced sensor integration for enhanced flight control in UAV-based construction automation. In this paper, we will briefly recap the construction surface finishing task here. So there are some critical challenges facing the construction surface finishing task. For now, it's heavily relying on low productive manual process. About 25 of these works are carried out on heavy machines like the powered trowels, and about 75% is on manual method like the hand tools showing the image. And the productivity has been stagnant since 30 years ago compared with other industries. And we also see that the worker safety issues and the health risk is another problem. There are about 55 hazardous substances can be found in construction surface works. And the OSHA estimated that there are about 2.3 million workers that are exposed to these risks every day. Another problem is inadequate defect detection and inconsistent quality control problem. Actually, the construction surface finishing work requires a high quality standard in surface finishing, including the surface roughness, waviness, and surface strength. And also it has a high aesthetic quality, durability, functionality, and sustainability requirement. So luckily, in recent years, we have seen a rising in robotic solutions as an automation solution in construction. The construction robots revenue and shipment has been ever increasing. And among them, the drones now thrive in many construction tasks. So as we see in the previous presentation, the drones can perform agile movement and collect real-time data with different sensors. That's why we want to use drones in this case. However, there are some current limitations. As we see that the drone market is rising in construction. However, the applications is limited to visual inspection and monitoring. About 80% of them are used for monitoring and quality control. Just 20% of them are used for measurement and communication. So there is no drone involved in any direct automation task in construction. Because there are some certain challenges faced by the drone application. As I explained before, we assume the drone to have a static payload, but in construction finish work, we need a rotary payload. But there lacks an integrated sensor fusion and adaptive control strategy, making it difficult to maintain a stable flight and a precise navigation in such kind of a dynamic construction task. So therefore, we can conclude that our knowledge gap here is that the existing system often lack the adaptability and the precision needed to maintain a stable flight in dynamic, cluttered, and disturbance-prone environment. And this limits their effectiveness in close-range, high-precision automation tasks like the construction surface task. Hence, our objective here is to develop a multi-sensor fusion and control framework that integrates multi-sensors and reinforcement learning techniques to enable precise localization and real-time stability control for UAV operating in dynamic construction tasks. Now let's move on to our method, where we designed an advanced drone-based multi-sensor fusion and control framework. And first, we collect the data from the LiDAR and IMU, and we use this kind of visual odometers and we use the simultaneous localization and mapping mechanism to localize our drones in a loop. So this map was generated by the method which we introduced in the previous paper. And this paper's main point is about this reinforcement learning-based stability control framework. So here we use, we have an actor and critic network. The actor network will make decisions based on the environment and the drone state input. The critic function will judge the quality of the action based on the environment information. And then we use policy gradient to update both of these networks. And we use a replay buffer to store essential training information and allow for more efficient training process. So with this module, and our map from the previous step, we can control the drones, and so to control the drone's pitch and roll motion, no, pitch and yaw motion here. So yeah, then in that case, we can stabilize the drones to make it to be kind of adaptive in this kind of task. So for the experiment, first we can see the system design with rotating disk and surface task. So here in the middle, we have a 6 degree of freedom gimbal system, because the normal gimbal system for cameras and they are often used on the drones that are not very suitable for our case. So we need to develop our gimbal system that's a straight gimbal. And so we 3D printed the different parts in real life. And we also designed a realistic digital twin in the simulation environment. And we have 2 experiments here. So the first experiment with rotary payload for enhanced flight control. First, our drone is deployed into a complex and confined space. We intentionally introduced some wind gust and load shifts to the drone system. And there is also a chance for potential collisions to the environment. Then, so ideally with our system, the drones can, after the disturbance, it can recover to its initial path and recover from this disturbance in a short period of time. So in another experiment, that's the same experiment as in the previous paper, that's a concrete finishing task. During this task, the drone will contact with the surface, it will have some vibration, and there will be some wind disturbance. And so in this case, we still want the drone to maintain a stable flight. And so here we show some results for this enhanced flight control under different conditions. Just to recap, our objective here is to develop a multi-sensor fusion and control framework to enable precise localization and real-time stability control for this UAV. And so we can see that for the recovery time in different conditions, it can recover in 2 seconds. And the orientation deviation for the payload is all below 3 degrees. And the trajectory deviation is less than 10%, which is good. And the force compensation, which means the how much of the force from the disturbance is compensated, is about 100%, which means almost all the force has been compensated by our system. So in conclusion, so our major achievement here is a robust stability under construction disturbance. The integrated sensor fusion framework enables the drone to recover within 2 seconds, and with orientation deviation below 5 degrees, and force compensation rates reach up into 98%. And the robustness of this system also reduces task completion time, increase load handling capacity, and stabilize the performance under different conditions that can commonly occur in construction environment. There are also some future directions, as we were mentioned about. The dependencies on the accurate sensor data and the computational demands of RL training may limit the deployment speed in diverse environment, and also still we need to explore more real-life behaviors in future research. And at the end, I would like to thank my lab mates, advisor, and all funding resources. Thanks for listening.